Hello all and welcome back to this course on computer organization. So in this lecture, we are going to look at the brief overview of the X86 instruction set. Okay. So before we jump into the specifics of the X86, in general, any microprocessor does not perform any operation without the relevant memory. Okay. So every microprocessor is in some way or the other interfaced to a memory as shown here. So you have the microprocessor that has an address bus, right? A bus is nothing but a bunch of pins or wires, right? So this could be a 32-bit address that goes to a memory, okay? And if you assert the write signal, then whatever address has been given and whatever data has been sent out from the microprocessor on the data bus, right, as seen here, which says data, the data bus could also be 32-bit for example, right? In the data that has been sent will be written into that particular address, right, of the memory. So, if I go back to this picture here, right? So, this is a microprocessor, this is a memory, okay. I have the address which is a bus, right, and the address is actually just an output pin for the microprocessor. It's an input to the memory, right. But on the other hand, if you look at it, data is bidirectional, right. This is data, okay. So this could be n bits, m bits and n bits. That means the address is m wires, data could be n wires. Typically m will be equal to n, okay, but it's not necessary. Then you also have the read and write signal. So both read and write are basically right. So if you assert the write, then what will happen is the memory could be simply be viewed as an array, right, as an array. So into the memory, right, of whatever address that you gave, you will be writing the data. So the assumption here is that the data width of the memory is n bits, okay, and the address there are 2 power m addresses that are accessible, that are that you can read from or write into this memory, okay. So therefore this is basically the operation of writing. And what is writing? Basically it means you give a certain address, give a certain data and then you assert the write, okay. On the other hand, if you want to read it, right, if you want to read, then you will give an address, you will then assert the read, then you will get on to the data bus whatever is in that address. This is called reading. Okay, this is called reading, and essentially that's why the data n bits that we saw here is bidirectional nature. The arrow goes both ways, because when you are writing, the microprocessor is giving you the data that needs to be written into the memory. When you are reading, the memory is giving you the data and that is going back into the microprocessor. So that is a bidirectional pin. That means it could be an input pin or an output pin depending on whether you are doing a read or a write, and that needs to be configured appropriately in the microprocessor, right. So what is the kind of memory that we are going to use? We basically have what is known as a logical map of the memory, and this has to be byte addressable, okay. Shown here for example is in hexadecimal 4 hexadecimal digits, which means it's a 16-bit address. So depending on the address that you give, I can store some, again, because I told you typically n will be equal to m, I can assume that the data is also going to be 16 bits of information. But when you increment the address by 1, that means it goes to the next byte, right? And therefore, I should be able to access the next byte of information. Okay, so this is important. So, if you look at this whole idea of a memory, right? So let us look at this memory here a little in some more detail. Okay, so what is going to happen is I can, I have my addresses like this, right? And I told you that the address could be m bits, right? So this is 0, 1 all the way to 2 power m minus 1. These are the locations in the memory that I can read, and each of these could translate to n bits of information. Let us say that n is equal to 32. Okay, then what will happen? I will basically have 4 bytes of information available from each address every time I access this memory. Okay, this is my memory, and I will get 4 bytes of data. So D0, D1, D2 and D3. So when I read memory of 0x00 all the way to m zeros, right? I am going to get D0, D1, D2 and D3 from the memory. Now this is 32 bits. Okay, so physically the memory might be organized like this, but however what we want is the memory to be byte addressable. That means when I give a certain address, I should be able to get a byte of information out of that. Okay, so for example, if you might read the memory might give you 32 bits out of that, but I should be able to access either D0 or D1 or D2 or D3 as separate bytes, and that is what we call byte addressability, right? So for this reason, what you can do is, the way to implement this we will discuss later, but in general this memory, let's say n equal to 32 here, I can define a logical map which is as follows. Each address gives me just 8 bits of information. Okay, so instead of D0, D1, D2, D3 being stored like this, it would be D0, D1, D2, D3 and then so on. So when I actually want to when I give address 0 and select only these first 8 bits, I will get D0 out of that, right? So in some sense this addressing now will be m plus 2 bits, because I need now to tell me which 8 bits I need from this 32, right? So I'll give an m plus 2 bit address and I will get my data is equal to memory of address of m plus 2 minus 1 colon 0. Okay, so this concept is what we call the logical memory map, and that allows us to access data, access it in a byte addressable manner. So forget about how the memory is physically organized. Just think that you have some m plus m bits of information. For every address increment that you do, you will get a new byte of information from the memory, right? This is the picture that we need to keep in mind in order to understand the microprocessor as we go forward. Okay, so what is the 8086 architecture, by the way, and what is this whole, we use the word X86, right? So let's just look at the history, right, of X86. So they started with an 8085 microprocessor, okay, 8085 MUP, which was 8-bit, somewhere in the 80s. Soon after, they made it 8086, which became a 16-bit microprocessor. Okay, I'll tell you what this 8-bit, 16-bit and all is in some time, right? Then they started, the 80, 186, 286, 386, right? So all this over due course of time, it became a 32-bit microprocessor. Okay, and so in order to provide some backward compatibility, they made sure that some of these assembly instructions that were executable on the 386, 486 and all that could still go back all the way to 8086 as long as that instruction was still a 16-bit instruction. Okay, so I'll explain to you what 16-bit and so on is. So what is X86 is basically a class of microprocessors which has a very similar instruction set. Okay, so it's not just one microprocessor or one particular processor from Intel. It's a class of processors that follows a certain complex instruction set architecture, right? So if you look at the block diagram of the 8086 architecture, right, it's a 16-bit microprocessor, which means that all the operations, right, are going to be 16-bit operations in the microprocessor. Okay, so when you want to do, for example, addition of two numbers, you will do a 16-bit addition plus 16-bit addition. Okay, however, because 8085 was 8-bit, they also allowed some 8-bit access. Okay, that's why you see, for example, this registers AX is being accessible as AH and AL and so on, right? So in general, the block diagram of a microprocessor is shown here. As I told you, the address bus from the bus interface goes out as an output pin, which is an address, some m bits. Then the data bus is bidirectional. It can either send data out or receive data from the memory. And then you of course have a control unit, which is also a control bus, because some control signals are not just specific to the microprocessor. It can also be used to control something outside or provide information about its control state to the outside world, right? So apart from this, the heart of the microprocessor is basically the arithmetic and logical unit, ALU. Okay, this is where all the arithmetic or logical operations are performed in a microprocessor. The control unit is what decodes instructions and it controls the execution flow, right? What is this execution flow? How does it decode? All that we will look at later. Okay. Registers are, again, I would say, the most fundamental unit of a microprocessor, right? In some sense, they are like a very, very small memory. Okay. So what is a register? Basically, if you look at a register, right, it's nothing but a bunch of flops. So what is a register? It's a bunch of flip-flops. Okay, this is a clock. And which flip-flop? Not JK, not RS, nothing. It's a D flip-flop, that's all. D and Q. Okay, so when the clock goes high, there is some data that will get latched from the input to the output, right? That is a flip-flop. Now you just take a bunch of such flip-flops and put them together, right? D, so D0, Q0, D1, Q1. For example, if I want a 16-bit register, I just need to put 0, 1 all the way to 15. So I'll give D15, I'll get Q15 out of this. They are all controlled by the same clock as shown here, right? So when the clock goes high, 16 bits of information will go into this register. So this whole block here is what we call a register. More specifically, it's a 16-bit register. So when I said that the microprocessor was an 8-bit microprocessor or 16-bit microprocessor, it meant that the register size, maximum register size was 8-bit or 16-bit or 32-bit, right? So that is what we did here. And the microprocessor, of course, is not going to give you access to an infinite number of registers. It has a very small set of registers. In fact, the X86 basically has only 4 registers, general purpose registers, okay? AX, BX, CX and DX, okay? Now, there are a few more registers called CS, DS, SS and all. I'll come to that later. But these registers are typically, at least one register has to be an argument for any arithmetic or logical operation, okay? The second operand, for example, if you are doing A plus B, one of them has to be a register. The second operand can be memory in the X86 architecture, right? There is another important register called the flag register. What is a flag register? After every arithmetic or logical operation that you do, there is a certain state that you can set. For example, if I have the register had a value 0001, right? And I just decremented it, the register value would come down to 0 and the 0 flag would get set. Okay, it's basically an indication of some specific interesting conditions, because based on these conditions I can choose to alter the execution flow of the program. In fact, to give you a very obvious hint, this is how if conditions are handled, this is how while, for loops and all are handled in your C programs. They ultimately translate to some flag being set and then you alter the execution flow of your program based on these flags, right? So this is the basic idea. So coming to the registers, by the way, I told you earlier, the register were AX, BX, CX and DX for the 16-bit microprocessor. But when they went to the 32-bit microprocessor, all they did was to call these registers as extended AX, EAX, EBX, ECX and so on, okay? So if you look at this, the X86 registers, right? So it is like this. This is AH, AL. This is what 16 bits, right, together is what we call AX, okay? And the 32 bits together is what we call EAX, okay? So the important thing is that the X86 instructions allow you to access the lower 8 bits, the higher 8 bits of the 16 bits or the entire 32 bits, okay? So I could address these registers as E, AL, AH. I can address the 16 bits together or I can address the 32 bits together, okay? Likewise, exactly the same thing would be done even in, this is EAX, would be done for BX. So BH, BL, and this is EBX. Okay, same thing for CX and DX as well. CH, CL, DH and DL. ECX, EDX. Okay, so you can do similar access for all the A, B, C, D registers, lower 8 bits, the higher 8 bits of the 16 bits, total 16 bits, or you could access the 32 bits. So this would be 8 bits, this would be 8 bits, this would be 16 bits, or this would be 32 bits. Okay, like I told you, this lower 8 bits and all is provided to you in order to provide backward compatibility to their 8-bit microprocessors. Okay, so that's the basic idea of this thing. In this course, right, we are not going to worry about these 3 cases. Okay, unless otherwise mentioned, we are not going to worry about this. We will simply assume all the registers are 32-bit registers and we are going to call them EAX. That's all. Okay, or EBX or so on. So from a C programming perspective, the registers are, though the registers are general purpose registers, right? In the sense they can be used for any ALU operation and so on. From a C programming perspective, some compilers specifically use these registers very specifically for certain tasks. Like EAX is used to store integer return values. We'll come to this later. ECX is used to store counters in loops. When you do a for loop and all that, this will kick in. There's one more very important register which is not a general purpose register, right? So general purpose register is available for any use. It's like a variable. Like in C, you can, inside that variable, you can store whatever you want. You can do whatever you want with that variable. Like that, the register also is available for use to the programmer to do whatever they want. On the other hand, there is another specific register called the EIP, right? EIP is the instruction pointer, right? Instruction pointer is what is going to point to the address of the next instruction. Okay, so the way this works is, when you have a microprocessor, right, like I told you, you have the mu p, you have the memory, right? The address, the EIP is actually going to tell you where the next instruction is, right? So what is stored in the memory? So this is called a code memory because it's actually storing the code or the program. Okay, so you are going to store some binary encoding of an instruction in the memory, and you are going to tell the microprocessor, start at this location and start executing this program. Okay, so for example, in this memory, I could have 0x0011 something. Okay, so I say load my EIP, okay, with this address location. Let's say this address location is 0x00000, okay, and the data that is stored inside that location, I am going to assume a logical memory map here. So I will precisely put 8 bits here, right? So in my EIP, I will simply store the address of this first instruction. Which one? This is the address I am talking about, right? So load 0x00000 and say start executing this program. So what the microprocessor will do is, it will read this memory location, it will try to understand what that instruction is, execute, and then it needs to know where the next instruction is. Now if the address of the, if this is where the first instruction was, then it knows that, let's say this is let me put this as okay, I can say 0x actually, right? I'm not worried about the so even though it is byte aligned, this 0x0011 0x0011 actually is going to take 32 bits. So that means the next instruction is going to be available 4 locations down. Okay, so it will be 0x000 all the way to 4. Right. So first 4 locations have been occupied by this instruction that was sitting in memory. The next instruction will be here 0x0110 0110, right. So the microprocessor, when it fetches this first instruction here, this particular instruction, it knows that that is occupying some 4 bytes in memory, and therefore the next instruction will be accessible only 4 bytes later, and therefore the EIP was initialized to this value, it will be incremented by 4. Okay, so automatically. And so we will do all the implementation of this exactly this in the second half of the course. But the EIP therefore always points to the address of the next instruction in memory. Okay, and therefore that's a very special purpose register and cannot be used for arithmetic and logical operations. If you go and modify the EIP, you had it, right? The code itself will get messed up completely, right? Likewise, there are 2 other registers called the stack pointer and the base pointer, right? Basically, the stack pointer is implicitly changed during the call or ret instruction. The BP is used to access local variables and function parameters. Okay. Now, EBX, by the way, is a very general purpose register. ESI and EDI, right, are the source index register for string instructions, right. So, for example, when you want to do a mem copy, right, you will see that these registers get used because you are going to point to a source index, destination index and say copy from here to there, right. So, these instructions are implicitly used by the microprocessor to execute such instructions, right. EDI again is the destination index register for string instructions. Now, EFL, like I told you, is the flag register, okay, it's the extended flag register with 32 bits. Like I told you, when it goes to 0, the 0 flag will be set. If you do an addition and a carry out is set, there is an overflow or a underflow or something, the carry flag will be set and so on. So, you can use these flags in order to do something different depending on the operands. So, this is a very conditional execution. So, like I told you, the microprocessor knows where the next instruction is, right? But I can also make the microprocessor go to a very specific location for something depending on the operation that I do, right? So, like that's what you do in a for loop or a while loop, okay? So, all that is enabled through the flag registers. Now, the segment register is used to point to some segment of the memory. So, like I told you, the memory is very generic. It's used to store all kinds of data, but you could store code, you could store data, you could store something in the stack, and so on, right? So, therefore, the memory, logical memory map might be common, okay, might be some 32-bit access, but the memory can be segmented into different regions based on this segment register. So, we will come to this a little later. The EDX register, okay, is basically specifically used to store the high 32 bits of 64-bit multiplications, okay. See, for example, when you do addition, right, of a 32-bit with a 32-bit number, you can at most get 33 bits. So, the 32 bits can be stored in a register. The 33rd bit can be indicated in the flag register, whether there was a carry or an underflow, if it is a subtraction and all that stuff, no issue. On the other hand, when you do multiplication, right, so addition or subtraction, you can start with a 32-bit register and eventually finish with a 32-bit register with the additional use of this flag register. So, I just need 32 bits for all the operations. But the moment you start doing multiplication, a 32-bit into 32-bit can result in a 64-bit answer, right? And therefore, that requires 2 registers now to store the answer, right? And which is achieved using this EDX. So when you do some multiplication, EDX will store the higher 32 bits always, okay?